This talk is about object support for GPU programming. And I'm going to talk why object support can be useful and why it is not easy to support and how we realized such a support. And first, let me begin with my talk with acknowledgement. This talk is based on the work in collaboration with the past and current members in my group listed here, and also supported by 2 funding agencies. So it's about GPGPU, general purpose computing on graphic processing units, which is becoming quite popular since late 2000s. And the idea of the graphic processing units can be considered as a many core processors with thousands of cores. But the notion of cores are slightly different from the CPUs, which requires the different types of the optimizations, by the way, and which will become very important when implemented our systems. And the general purpose computing part means the computation other than drawing graphics. But the currently main application domains are supercomputing. For example, 8 out of top 10 fastest supercomputers are actually using GPUs. And the other applications are usually problems with regular parallelism, like image processing or deep learning. But we believe this application domain can be much wider. And in order to do that, we believe that the object-oriented programming will be useful. But before talking about the object support, I'd like to say that the GPU programming is fun because it reminds me the days of touching bare machines. And in order to explain my feeling, I'm going to explain one optimization technique for GPUs by borrowing the slides from NVIDIA. The slides are titled Optimizing Power Reduction in CUDA, which is quite old, published in 2007. And the reduction is a computation that reduces many values by applying operators until we get the one number, and which we can often found in some computing sum, products, max, and so on. And since those operations at each stage independent each other, so we can easily parallelize such computation by just assigning threads to each data element. But this is not such a simple in order to get the better performance on GPUs. So this diagram illustrates the computation in the first naive implementation, where each here is data, and those circles denote the threads assigned to each data element. And then at each stage, those threads compute 2 values into 1, and then half of the threads do the same thing until we get 1 value. But this naive implementation actually have a performance problem. If we look closely at this computation stage, then those 2 threads, active threads, are numbers having a thread ID 0 and 8. That means those two threads are interleaved with respect to the thread IDs, which is quite inefficient because of the lower core utilization at the hardware level. So this program can be optimized by reassigning the threads and the computation in this way. So in this implementation, thread number 1 computes those elements, and the next step computes on those elements, and so forth. And then we will see the consecutive IDs of threads are computing at each stage, and which gives the 2.3 times speed up already. But still, this implementation have some inefficiency called bank conflict. So if we look at this computation stage, then the two threads are reading the memory addresses distant by power of 2, which causes a bank conflict, which can be a source of the overhead. So we again rewrite the program to change the reading and writing addresses so as to all the threads are going to write the consecutive memory addresses. And then we will get the another 2.2 times speed up. Then we can do more optimizations, like combining a load and add operation, fast load and add operation, and unrolling some computations, and do more aggressive unrolling. And in the end, we will get the 21 times speed up from the original naive version. This is very interesting. By the way, I would like to note that we can learn two important lessons of GPU's performance characteristics from the previous slides. Both are about locality. And the first lesson is to allocate tasks to threads with consecutive IDs. So if we are going to assign tasks, then this allocation is good, while this scattered assignment are bad for performance. And the second lesson is when the multiple threads going to access the memory addresses, then they should access consecutive memory addresses like this way, rather than that way to the scattered addresses. So those two lessons are actually important to make design decisions our language that I'm going to talk today. So GPU programming is fun, as we can improve performance dramatically by applying low-level tricks. But this is also painful to do so, because applying those tricks ended with programs like Fortran style, meaning that all the data should be allocated in global arrays of primitive types, and we cannot do any static data allocations, which is not so fun to me. So what we'd like to do is to introduce higher level programming abstractions for GPU. And in my case, those abstractions are object-oriented programming and a taste of scripting language. So we are developing 3 domain-specific languages called Dinosaur, Ikra, and Sanajay. And Dinosaur is an object-oriented programming support for GPU based on C++, and Ikra and Sanajay are scripting language support for GPU based on Ruby and Python. And if you are a functional programmer, then I'm sorry about that. But there are also excellent studies to provide a higher level functional abstract to GPGPUs like Accelerate project and Lift project. So you can take a look at those projects. And the underlining techniques are pretty common with those languages. Okay, why OP can be useful to develop GPU applications. Let me explain this idea by showing the example programs that are written in Dinosaur first. Those applications are N-body simulation, traffic simulation, fish and sharks, and Burns hat. So the first application program is an N-body simulation, which simulates movement of bodies driven by mutual gravitational force. And the algorithm is very simple. Each body represented by boxes in this animation computes the gravitational force from all the other bodies and then updates its velocity and position by summing up the gravitational forces. By the way, this video was recorded by running actual GPGPU programs that perform simulation and visualization at real time. But actually the most time of the execution was spent for the drawing of each application. So you cannot determine the performance of GPU computation from this animation. Anyway, what kind of programming concepts are useful in this application? And then first thing we can notice is the source of parallelism comes from the many bodies. So in N-body simulation, by performing the force calculation and the position updates for each body in parallel, we can get the parallel speed up. So we need some support for applying the same function to many object bodies. And another useful concept is object-oriented modeling. We can consider each body in the system as an object that contains its position, velocity, and mass. So this is a typical example where object can be useful when we are modeling this kind of problem. The next example is traffic simulation, which simulates the movement of vehicles on the streets in a city. And I forgot which city it was, but it was taken from the OpenStreetMap database. And then by moving cars or buses on the street or based on some rules, we can observe how traffic flows smoothly in what part of the city, and what part of the streets can tend to have traffic jams. And if you magnify the map, you can see small dots, red and blue dots moving around. Those are cars or buses. And the color of vehicle should correspond to the type of vehicles. And then streets are also painted in two colors, three colors, white, pink, and dark pink. And those are also representing a different type of roads. So in this traffic simulation, the source of parallelism is from many vehicles running around the city, which can move independently. And in this simulation, object-oriented modeling is more useful because there are many different types of objects in the world, not only the vehicles, but also road segments and traffic lights and many other control systems. And those are referencing each other. And if we draw a class diagram for this application, then there are already 7 key classes exist. And actually it is and notion of class and inheritance is also useful in order to express different kind of roads and different kind of vehicles. So OOP concepts are pretty useful in this simulation. The next application is an agent simulation called Fish and Sharks. And this screen represents a big ocean divided into small areas. And in each area, there can be a fish or shark shown as green and red dots. And both fish and shark moves randomly, and the spawn eggs and increases its population. And sharks will move randomly and to eat fish when they encounter fish or die by starvation. And then we will see the increase and the decrease of population of fish and sharks through the simulation. So the same as the previous applications, the source of parallelism are from the agents, in this case fish and sharks. And the classes are also useful to express the similar behaviors of fish and sharks, and also the different behavior of fish and sharks. And if we add more different kind of fish or sharks, then classes are more useful. But there's more interesting point in this application where where fish and sharks dynamically created and deleted. So this is pretty common in object-oriented languages to create new objects and delete objects when it is no longer needed. So please note this point. And then the last example is Burns Hat, another n-body simulation that uses much faster algorithm in terms of computational complexity. And the idea of the algorithm is to approximate forces from distant bodies by using a spatial tree, which is represented by those blue boxes in the animation. And the tree structure is created, so that tree structure is created to accommodate at most one body at the leaf level of the node. So if there are dense area in the universe, then the tree depth of the tree becoming very low, very deep. And the source of the parallelism in this simulation is similar to the naive version of n-body simulation, but in this case, a leaf node which corresponds to each body. And on this part, this is not so different from the naive version of n-body simulation. But the interesting point in this simulation is the use of the spatial tree, and the shape of the tree changes dynamically according to the movement of the bodies. So if one body moves to the another area where the other body exists, then we need to create we need to extend the spatial tree. And if the one body moves away, then we need to delete a tree node. So we need some mechanism of the dynamic creation and deletion and maintenance of tree structures in parallel. So we've seen that in those 4 examples, applications, and then the notion of OOP can be useful. But so far, OOP is not so widely used on GPUs. Why is that? this can be explained by difficulties to realize efficiently realize those 3 points, namely dynamic object creation and deletion, faster memory layout, and access to all objects. So let's see those 3 difficulties in more detail. The first one is dynamic object creation. Actually, typical GPU programs are written in this way. First, CPU allocates the n elements of data on GPU, and then CPU spawns n threads on GPU, and then each thread processes each data. But if we want to support, we want to do dynamic object creation like we've seen in fish and shark simulation, that means this parallel process requires to allocate new object. So that means we need to create new object inside of the CPU rather than allocating the memory area by CPU. This is not actually easy because in order to achieve the locality. So assume there are many threads are running in parallel, and there is a big heap. Some part of the heap is already used, and the other parts are empty. And those many threads are running the same function, and some of them requested the new object, meaning the new memory allocations. Then what we needed to do is to pick up the unused memory addresses and assign for each memory allocation request. So, but the difficult point is we need to allocate distinct addresses so for each request. And also, in order to achieve efficiency, we need locality. That means we need to squeeze those requests into consecutive memory addresses, which is actually a sequential process and very difficult to parallelize. Second difficulty is faster memory layout. As I said before, memory address locality is crucial for performance. And sometimes this characteristic is called memory coalescing. But the objects are the enemy of locality for GPUs, which can be explained by the term called array of structures and structures of arrays, which I'm going to explain in the next slide. So the array of what is array of structures? This is a normal memory layout in object-oriented languages. If you have a one class declaration called fish, which has 4 fields, P, NP, ST, and TI, and if we create an array of fish, and then those fields are allocated on memory in this way. So the first field of the first object, second field of the first object, and third field of the first object, the fourth field of the first object, and then first field of the second object, and so on. But with this memory layout, if many threads performs the same instruction, for example, increment TI field of all fish object, and then the memory access actually happened on the TI field on each fish object. That means the interleaved memory accesses or scattered memory accesses, which is inefficient, as I explained before. So in order to get better performance, we'd better to lay out those data in this way, which is called structure of arrays. That means each field is an array of all objects, and So if there are 4 fields P, NP, ST, and TI, then we allocate the all P fields of all objects first, and then all NP field of all objects second, and so on and so on. And then if all the threads performs the increment of TI field, and then the access to the memory is going to be consecutive addresses, which gets better performance on GPUs. So this is faster implementation, but not actually OOP, but we actually allocating arrays, global arrays of fields. So we lose object orientation here. The third difficulty is to access to all objects. As we've seen in the example applications, the source of the parallelism is the set of objects. And some applications do the dynamic object creations. In such a case, we need to include those newly created objects in the next step of simulation. So, so that means the dynamic object creation and deletion must be fast, efficient, but also supports the efficient access to all objects, which is not actually easy, because and actually, if we manually maintain an array or list of all created objects, and then the overhead of managing such a list or array is going to be very high. So I have explained 3 difficulties on supporting objects on GPUs. And there are actually some existing work that addresses those difficulties in part, but we found that none of them are sufficient and solving all the 3 problems. So there are parallel memory allocators for GPUs. The one is CUDA-malloc, which is an official library from NVIDIA, but this is extremely slow, and I never recommend you to use this library. The other allocators are called malloc-mc and halloc, actually do the fast, efficient memory allocations, but they do not support structure of array layout and also the access to the all objects. And there are also libraries that transform class declarations into structure of array memory layout called SOAX and ASX, but they do not support dynamic object creation. And if we want to support dynamic object creation, then we would probably need to rewrite or redesign entire library. So we developed a domain-specific language called Dinosaur, which is actually a C++ domain-specific language for GPGPU, implemented as a template library, where you can write C++-ish OOP programs. And Dinosaur supports the parallel object creation efficiently on GPUs, and it also supports the structure of array faster memory layout, and it also provides the efficient do-all operations that accesses all the created objects efficiently. So let's see how Dinosaur program looks like by an example. This is a part of fish and shark simulation written in Dinosaur. And I'm only showing 2 classes, namely agent and fish. And agent is a base class of fish and sharks, and this class declaration requires a few lines of the special syntax to declare fields and other information. So this is not compatible part of the standard C++. And field declaration also requires a special syntax because of the we need to do some transformation. But the we can also use the many existing features of C++ without requiring special syntax. For example, we can use inheritance. Fish, we can declare fish as a subclass of agent by inheriting the field declarations and the method declaration from agent class. And we can also define a method as usual. So this is an update function that moves fish for each time step. And inside of the method declaration, you can freely access object fields and also the fields of the pointers fields given another object fields by given pointers, and you can also call methods or on this object or another object. And we can also, and importantly, we can also do the dynamic object creation inside of the method, which is called executed on GPU. And the CPU code in the fish and shark simulation actually simply calls the update methods on fish and sharks iteratively, but we actually provide a special API to do so. So it's called parallel do, which receives the class name and method name, and then the runtime system will enumerate all the fish objects created so far and responds their threads to execute the update method on those fish objects inside of the GPU. So let's see how Dinosaur supports those OP features in an efficient way. And the key ideas can be summarized on those 4 points: SOA in block-based management, hierarchical bitmaps, pointer mangling, and compaction. And I'm going to explain only those 4 points today, and let the compaction leave. So first, SOA, structure of array in block-based management. And the first one is block part. We divide the entire heap into the same size block, and then dynamically assign each block to a specific one class. In this case, like this block is assigned to fish class, this one is assigned to shark class, this is not yet used, and so on. And each block stores up to 64 objects of the assigned class. And the number of objects can be allocated stored in a block depends on the size of the class. So at the higher level, by dynamically changing the assignment of a block to classes, we can achieve the dynamic memory allocation. And the SOA part works in this way. So we use structure of array layout only inside of a block. So if we assign this block to fish class, and then the inside of this memory block is divided into 4 memory areas corresponding to the fields of fish class. And the first part is a P field for the all 64 fish objects allocated inside of this block, and so on. And so this guarantees the coalesced memory accesses inside of the block, and by using bitmap, extra bitmap information which indicates which slot is actually allocated by actual object or not, we enable the dynamic allocation of objects. And the next idea is hierarchical bitmaps. We manage those blocks by using bitmaps on a per class basis. For example, this is a bitmap of blocks for shark class. That means if there's a flag in a bitmap, then this means this block is assigned to a shark class. So by using this, we can very quickly find the available block for each class, and also we can also enumerate. We can do the do-all operation very efficiently, only to blocks assigned to a specific class. And these bitmaps are needed to be updated concurrently, sometimes in some cases. So we use atomic instructions of the hardware level atomic instructions for updating to maintain consistencies. And the actual memory allocation algorithm taken place in this way by using those bitmaps. First, many threads started requesting allocation of objects for class C, and then the first thing to do is to combine requests on a per 32 threads group, which is a magic number in GPUs, and then the representative thread of each 32 threads group randomly walk down the C's bitmap to find an available block. And then when they reach a available block for class C, and then that thread occupy empty slots by modifying the bitmap inside of the block, and then the allocation is done. And in some unfortunate situations, the two threads are going to trying to allocate in the same block, which causes a collision. And in such a case, then the atomic operation will decide the loser, and the loser thread will need to go in to do the same operations, random walk process again until they will find an available block. And finally, if needed, then they walk up the tree to update the bitmap information. And in this algorithm, we use the random walk processes. So that actually makes the lower level of contentions, which guarantees the fast allocation. And we also use only we guide those threads to find the available block. So that means the already allocated block for class C. That will guarantee in the long run, then those threads going to fill a block for particular class. That will give the better memory locality. That's the basic idea of the efficient memory allocation. And the last technique used in Dinosaur is pointer mangling. The question here is how to access a field of an object when an object is allocated in a certain slot of a certain block, where fields are laid out in structure of array manner. And then what we did is to encode the block address and the the slot number inside of a block into 64-bit pointer, so that and by overriding the field access expression in C++, so that that expression will decode those information from the pointer like value and calculate the actual appropriate address for the field. And this actually requires only a few extra instructions and without no extra memory accesses. So this diagram illustrates how pointer mangling works, but I'm not going to explain in detail. I just only want to point out that the memory pointer is divided into 4 sections: slot number, block address, and capacity and type. And then the field access like this is actually needed to determine the block, and then the offset of the field array inside of the block, and offset within the array of that field. And all the information can be taken from the pointer information, so we don't need the extra memory access here. Okay, I have explained the implementation techniques and then how it is efficient. So we wrote several applications in Dinosaur and with other memory allocators to compare the performance. And this graph shows the execution times of those applications. And each group of bars corresponds to one application. This is Fish and Shark, this is traffic, and so on. And in each group, from left to right, a bar corresponding to the execution time of Dinosaur, and the other 4 other memory allocators, and the applications written without using dynamic allocations. And since the height of bar shows the execution times, we can see that the Dinosaur execution is faster than the other memory allocators. And by analyzing the breakdown of the execution times, we found that the Dinosaur is faster thanks to for enumerating the all object support, and also thanks to the structure of array memory layout. That means for example, in this Fish and Shark simulation, those white bars showing the cost of maintaining all fish and shark objects dynamically created, which dominates the execution time. And in Dinosaur, such operation is quite fast thanks to the hierarchical bitmap. And if we compare the only allocation time, then Dinosaur is not actually faster than the other memory allocators. But by running the actual application, then the Dinosaur actually is much faster in the computation part of the application thanks to the structure of array memory layout. So that's the source of the efficiency in Dinosaur. And if we look into the other applications, then in some applications, Dinosaur is actually faster than the programs that do not written without using the dynamic allocation. That means they allocate all the objects upfront of the execution. This can happen because in those static allocation version, we need to speculatively allocate the many possible objects which might not be used all the time. So with dynamic allocation, we can minimize the computation only to the actually created objects, which sometimes can be faster than the static allocation. Okay, so we made dinosaur DSL and confirmed it is useful. And the rest of the talk is um, about the adding a taste of scripting language to GPGPU programming. And the motivation here is quick prototyping of GPU programs like we do for CPU applications by using scripting languages like Ruby or Python. And here we also would like to integrate the GPU applications with existing libraries in those scripting languages, such as web scraping, JSON parsers, or nice visualization, graphical visualization libraries. And we have two ongoing projects called ICRA, based on Ruby, and the Sanajay based on Python. And ICRA, those two DSLs are slightly different, and the ICRA provides the map and reduce API on top of Ruby arrays. And Dinosaur is actually serves as a Sanajay is a dinosaur wrapper in Python syntax. Then I'm going to show a very small example for ICRA and Sanajay. And ICRA is a Ruby DSL for GPGPU. And this is an example program which is almost compatible with the standard Ruby, except for one class, PRA here, which designates that this array should be allocated on GPUs, and the computation map and reduce computation for this array shall be performed on GPUs. So the compiler detects those computations and transforms those blocks into the CUDA code and then executes on GPUs. But you can integrate with the existing normal Ruby libraries, which is executed standard Ruby interpreter on CPU. So, for example, in this case, we can easily visualize the result of GPU computation by writing a small amount of code. And Sanajay is a Python wrapper for Dinosaur. And our initial motivation is to help programmers like me who do not want to write C++. And so the syntax of Sanajay is standard Python, but requires type annotations like this. And the basic idea is to transform those class declarations into Dinosaur, but with also enabling several higher level abstractions, like inlining nested objects with structure of array layout, and kernel fusion and splitting, and first class object sets. So to conclude, in my talk, I have shown that the object-oriented programming can be useful and actually possible on GPUs. And in order to make it possible, we found that the locality-aware memory object allocation is a key technique. And we also see many interesting challenges around this area still remaining, like applying type ownership types to accurately allocate the memories, or the mixing the different memory layouts, and the abstractions for specific type of application domains, like graph processing would probably be useful. So the integration of such kind of abstraction is also a challenge, and the further optimizations specific to the applications, like object reordering, will also be interesting. Okay, so that's it of my talk.
Okay, thank you very much. Okay, so we are now open for questions. So I'm happy to take any questions either on Slack or on voice, if you have some. So we can wait for a moment. So perhaps I can start with a quick question. So you mentioned that basically, like your C++ syntax is following the C++ inheritance model. So how much of the C++ inheritance model do you support? Because C++ inheritance, it's quite complex, I think. So for example, you have multiple inheritance, virtual inheritance, and so on. Do you support everything? Are there restrictions? What is it that you support exactly?
Yes, thank you for the question. So I wasn't clear in my presentation, and it is definitely limited. So the single inheritance without virtual dispatch. That's the short answer. So basically you can create subclasses. That means basically means copying all superclasses, field and method declarations into subclasses, and you can use the same method definition, same superclass method definition native code to apply subclass, but we cannot do the virtual dispatch. So for example, we have two inherited classes, and there are many objects of those two classes. Then we need to invoke methods on each set of classes separately. So that's the basic restriction.
Okay. Right. So any other questions from the audience? Right. Maybe I can ask another one. So I was trying to. So I'm first of all, I've never done GPU programming, so I don't know much about GPU programming. But yes, so from your talk and also from some other talks that I've seen, my understanding is, yeah, so you have to do kind of normally you have to do static allocations like ahead of time. And obviously this creates lots of challenges, and you mentioned a couple of those. And I was just trying to understand, I was trying to get my head around like how your system works. And I understood that, yeah, so you have the blocks, and for each block you have a class that is assigned to this block. But how do you determine, or when do you determine which class is assigned to a block? Do you do it all ahead of time?
No.
Right?
Okay.
Like saying,
So the blocks are, each block is assigned to specific class on dynamically. So at the beginning, all the blocks are empty, and the first allocation request arrives. Then it's going to find available block for that class, and if it doesn't find any available block, and then it will take one empty block and then turn that block into for that class. So things go like that way. And when object is deleted and the last object of one block is deleted, then that block will return to be the empty block so that it can be used for other classes. Does this answer to your question?
Okay. So yeah, I think it does. I think so basically there's really a little bit of dynamic. So I guess basically what you implement is you implement this dynamic allocation management. So it's part of the language, right, of your language implementation. So I suppose you allocate the memory statically all at once when you start a program, but then you choose which things to put in each part of the memory as you go, as the program runs.
Exactly.
Okay. Okay. So any other questions from the audience? Let me just see Slack. Okay, so, oh, okay. There's one question in Slack, and the question is: can retry-based allocation lead to live lock?
Yeah, that's a good question, and the answer is no. And it's very hard to explain, but we carefully designed so as not to make any live lock or deadlock situations. Well, I think I can only say, yeah, trust me, or read our e-group paper, which explains how it cannot, it's safe enough. And maybe the question came from in this way. So since we use retry-based allocation, so if one thread comes to this block and then it cannot find any available slots, and then it's going to find another a new block again. And if unfortunate situation happens, then it needs to go up and if going to the same block. But every time retry happens, then it's going to eventually those hierarchical bitmap will be updated by the other thread activities, so it is going to be stabilized in any way. So I don't know, I can explain clearly, but that's basic answer to that question, I guess.
Okay, thank you. So any further questions from the audience? So perhaps I can just ask a quick follow-up question from what I asked before. So you said that the dynamic dispatching or virtual dispatching is not yet supported. Do you think it could be supported?
So by theory, it's possible, but actually the virtual dispatching is not in favor to the GPU computation model or hardware model, because basically virtual dispatch can be considered as a dynamic branch, and that causes the so-called thread divergence or warp divergence in GPU. So that actually makes the computation much slower. And in fact, the CUDA C++ version of CUDA actually supports the dynamic virtual methods by converting the virtual methods definition into conditional branches, and which is extremely slow. And so usually we don't use any virtual method course when we program in CUDA, but so for compatibility, I think NVIDIA provides that feature. But so in that sense, I'm not sure it is a good idea to support virtual method.
Okay. Right. We still have some time for maybe one or two final questions. So if there's anyone from the audience. Okay. I think perhaps this is it. So I would like to thank our speaker for this very nice talk. Virtual round of applause.
Thank you very much.
And